what it is, what it does, and a brief overview of what the architecture is. It's not too much time. We don't have a lot of time to get into the nitty-gritties, but we'll talk about how the architecture is today rather than how it's derived or what caused it to be derived in such a fashion. So we'll talk about how it's today, and hopefully you'll come to see a few advantages with it that are a little bit difficult to see at first, but once you see that, you'll realize that it's a lot more scalable and portable than earlier. So what is the SCP firmware? The SCP is the system control processor in ARM terms. So that's a power coprocessor or a power management controller, however you might want to call it, that will abstract your power management tasks and system controller tasks away from your main application cores. So this is compliant to the ARM SCMI specification. For those who don't know what the SCMI specification is, we have a talk tomorrow, and you could read up the spec as well. It's there. The core of the SCP firmware that we have is open source. You can find the link there. The slides have already been shared, and you can have a look at the slides as well, and you can go to the link. And the execution context is agnostic. So what that means is that the SCP can be run on any kind of environment that you wish to, any kind of hardware environment, any kind of software environment. And that gives it a lot of flexibility to be deployed in different circumstances. On the right-hand side, we have the formal definition of what the SCP software is. So that's what it is, and we call it the SCP. There's a term called the MCP as well, which is mostly for manageability control processors in the infrastructure domain. And the same code base can be compiled in both ways. So that's another point that we have. So overall, how does it look? This is the standardized way in which we have split the SCP firmware nowadays. It's in 3 parts. The advantage that we want to do is that we have realized that the firmware cannot be tied very specifically to a hardware if we do want everybody to deploy it. It's not a reference firmware anymore. You can actually take that firmware, deploy it on your platforms, add a few bits and pieces, and it'll start working. So at the lowermost layer, you see the architecture-specific implementations, which will basically give you the capability for interrupt and execution handling, threading, and memory management. Now, those are very basic interfaces and very basic functionality. There's not a lot to be done. Memory management right now is static. There's no dynamic allocation. There's no dynamic deallocation. It's all done through one very simple API. Threading is, as the name suggests, it's there, but we don't use a lot of it. So what that gives you is that even if you want to deploy it on a bare metal platform or on a platform where you have a microcontroller and an RTOS, but you say, I want to use minimalistic threading, even that will do. And interrupt and execution handling is mostly for your processor stuff. So an ARM processor will behave different from some of the architecture, but you could literally have your own architecture thrown in there and the code will still work. Everything above will still work. So you see below the architecture specific implementation is a framework, and the framework has a few functionality over there that you see, and the framework is completely product agnostic and architecture agnostic. What that means is the same. You take the framework, you push it anywhere you like, it'll just work out of the box. You don't need to change a thing over there. You just need to change your architecture-specific implementation if you're doing it on a new software environment or a hardware environment. That is, what are your interrupts? To enable an interrupt or to disable an interrupt, just the standard APIs that are needed, you'll just need to plug them into your architecture-specific implementation. Above the framework, you have your modules. So the way we define things now in the new SCP architecture is that everything is a module. So what that means is, suppose you have a UART controller, very simple example. That UART controller is a module. Suppose you have your own protocol. Let's say you have something to do with a very minimalistic network stack. You can make that as a protocol. Something like a DMC or dynamic memory controller can be another module. And if you notice the color codings, you'll notice that the modules, on top of the modules, there's a small green box called a config. So the configuration of a module is now very different from the module itself. What that means is the same module can work on different product-specific configurations. So let's say you have a module like an I2C driver that connects to your PMIC, And the configuration of the I2C driver is now product specific. So for each of your product, you just change the configuration data that gets fed into your module, and that does the trick for you. The module remains unchanged. So it's sort of like the way the DT provides configuration to a Linux kernel, although this is not DT compliant. This is another specific way in which it's done, but it provides you the scalability. There is a purple colored module that you see over there called module 2. Now that is something that's more of a non-product, non-architecture module. What that means is if you've got a standard protocol that you need to implement, something like, let's say, some portion of a network stack or any particular protocol that you have. So you could have a protocol as a module with a few configuration elements on top. And then on the third box over there, you see a module 3, which is further split into sub-modules below. So it has an element inside, and inside elements you have sub-elements. So there are a few connotations for that, which we'll come to later. What it allows you to do is that it allows you to build, for example, you have a PMIC, right? And your PMIC might have a sensor driver inside, a battery charger inside, and other stuff. So that's the way you can split your stuff. And even you notice that the elements inside a module can have their own configuration. So that provides a variable level of scalability to you. And then again, you see a module itself can have multiple elements, and each element can have multiple sub-elements. So this provides you a lot of flexibility to do as you please. Central framework is provided by the SCP firmware. It's open source. We have a reference implementation of the architecture specific implementation, the bottommost layer. We have that reference for a Cortex-M class device. That already works. And then you can go ahead and plug in your own modules. We have reference implementations for many of the FVPs that ARM provides. We have reference implementation for Juno, for N1SDP, and hopefully that should cover enough of your use cases to do whatever you want. We have also some upcoming reference implementations with some of the products that for the STM32 that are still to be merged, but those will also come online and you'll be able to see them later. So that's how it's overall organized. If we were to look a little bit deeper into the types of modules, you'll see that modules can be 4 types. Hardware abstraction layer, we all know what it means. I won't go into the details. It's the same as what it means. A driver, that means your module can be a driver like an I2C or whatever you think of it. It can be a protocol, as we showed in that purple box. That can be a protocol or a service. Service is something that provides a standard functionality for everybody else to use. It might be something like logging or some other thing that you might come up for your own product. And since it's all your own platform and your own product, you can choose to modify and implement it in a different fashion. Then comes the part about binding. So now we have got all these modules over there, a framework over there, and an architecture-specific implementation at the bottom. And now you need a way for this entire thing to talk together. Because how does a module 1, which might comes from a reference implementation of an X product, and a module 2, which comes from a reference implementation of Y product, how do they talk to each other? And that's where the part of binding comes in. This binding enables the module to talk to the framework and different modules to talk to each other as well. So one more part, combining product into the modules. If you look at the right-hand side, that is how we make an SCP image. So when you specify an image for your product, for your board, you have a product.mk file. Now, this might define 1 firmware target, 2 firmware targets. You might have a firmware that goes into 3 separate microcontrollers. You could have, so you will define each of your firmware targets. And inside each of your firmware targets, you will define what are the modules that you're compiling. And then you'll provide the module-specific configuration data. And all of this, when you compile, it builds in the number of firmware targets that you want to compile. So that means there are a few reference modules that are there already in the firmware open source code. You can add your own modules, combine or choose a mix and match of different things, and make your own module image. So that way you don't have to write the entire firmware from scratch. Things are already there for you. You just add the bits that you require. And any questions, you can please stop me at any point in time and ask. let's see. So now we'll go into elements. So as we discussed earlier, a module can be composed of one or more elements. So what that means is that an elements of a driver type module can represent an hardware interface that it controls. For example, you might have 3 I2C instances, so each of them might be an element. You might have a sensor device which consists of further groups of sensor devices, and that can be elements and then sub-elements below it. And elements are strictly optional. It's up to you. You want to define them, or you want to take each of these I2C devices, the different module, it's completely up to you. You define how the architecture fits you or how you like your stuff to be implemented. And elements, and you have to provide an element description as well, which is the configuration. And elements are defined by a structure, and this is the way it's done. So there are sub-elements, number of sub-elements within the element, and are pointed to the data in the module element format. So that's the generic way in which we are doing it. I won't go into the details of that because of lack of time, but you can look up the code. We have a lot of examples over there, and you will find a lot of configuration data for Juno or other platforms as well. Sub-elements specifically is a resource that's governed by an element. Sub-elements do not have their own configuration structure. So if you have sub-elements, you've got to make sure that you have a way to pass the configuration. We have done that intentionally because otherwise it becomes too many layers, introduce a lot of complexity. We don't want to go there. We do have examples in code where we have got sub-elements and elements. Hopefully you'll be able to figure out the way we have done it over there. So we have kept sub-elements restricted for that purpose only. And there's an example for you that you can consider a sensor HAL as a module, and PVT and thermal sensor drivers can be modules that use a sensor HAL, and the thermal sensors are arranged in every group, and each group can have its configuration, and each sensor in the group is a sub-element. So what that means is that if you have a PVT sensor and you've got, let's say, 3 instances of it, each of them can be a sub-element, and the PVT sensor itself can be an element, and then you have a big group of a module. So that's the way the entire thing can be set up. It's pretty flexible, straightforward, and it looks a little bit complicated when you look at it right now because it's set up in this XYZ hierarchical order. But once you see an example, you'll realize that's pretty simple. Okay, the next part. Now we understand what a module is. We understand how you can compile it to build a target. The next time is once you load it, how is it going to look when you run it, right? So the pre-runtime stage is when you start booting your firmware element, and then your runtime stage is once the execution starts. So the pre-runtime stages has 5 stages, sorry. One is the module init. So once the system starts, each of these modules will have an init function. So the init functions of the modules will get called just like Linux kernel. So there's nothing to explain over there. Then you have an element initialization. So as you said, every module will have every module's configuration data will contain the number of elements it contains, and then the element initialization hook will get called. So in your module, you can have an element.element in it, and that will get called next. And then you have a post-init function. So this is an optional stage. In post-init, typically it's some stuff that you might not have been able to do in the first phase itself. You push it to the next stage. That's, again, completely platform dependent. We don't use that a lot. It's just there for flexibility, and you can choose completely to skip it. Then there's a bind function. Now, this is the place where modules actually register with each other. So let's say you have a PMIC module that talks to an I2C module so that you can communicate with the I2C. So that's where you register both these modules with each other so that they can find out each other APIs and then talk with those APIs. Now, the beauty of this is, what it does is that you could have directly called one API from the other in the module, right? But you don't want to do that because your PMIC driver might come from somebody, your I2C driver might come from somebody else, or you might have 2 different variants of an I2C driver. You don't want to keep changing your files or putting hash defines inside it. So this allows for dynamic discovery of all the APIs that you have so that when you start booting, you discover the APIs yourself, and then everything just works out of the box. So the same code runs. You don't have to modify the code. You don't have to put ugly hash defines and so on and so forth. And then that's the start phase. When that gets called, that's like the final phase for the module to do something to start up the entire process when the system starts working after this to move into the execution state. So that's the final start call, and then in the runtime stage is a normal execution state, and you can have events, notifications, and responses generated and processed. I'll come to the last line, events, notification, and responses, what they are, what they're used for. I'll come to that after this time. I'll quickly do a time check. Okay, we're on track. Okay, before I do this, are there any questions, at least at this stage? Cool. Move on.
Don't you have several binding steps? I can't remember exactly in the SCP. You have step 1 and step 2 in the binding. Is it? I can't remember if it's in the binding or somewhere else.
The bind stage?
Yeah.
The bind stage is the fourth state. Yeah.
Yeah, but you don't have several levels. I remember that there was.
Yeah, there are 2 levels of bind.
Yeah. Okay.
Right, and I've not put them for the purpose of reducing the complexity over here. But then that's again, if you need 2 levels of binding, it's not mandatory. You can have just 1 level and do away with it. Yeah, you're right. Okay, so now we have started up the firmware. How does the execution work? So the complete philosophy over here on the SCP code is that everything is now abstracted as events. So let's say you have an interrupt that comes to you, and you handle that interrupt, and that generates, let's say, a bottom half of an interrupt, right? You can actually post an event as a bottom half. So once you post an event as a bottom half, you handle that event, and then let's say you figure out that you need to do some transaction on a bus, right? So that transaction can be abstracted as an event. You can generate an event and pass that event to a corresponding module which does that functionality. So let's say if the transaction is on a I2C bus, that's the simplest example I can think of, you pass that event to the, target that event to the I2C module. The I2C module picks that up, and then it processes that event, and let's say it figures out that, hey, for doing this, I need some extra data from another module. So the I2C event can then generate an event to the other module as well, and so on, so it goes on and on. So that's the smallest granularity in which we execute things on the new SCP code. It's in terms of events. Why it's not a direct function call? And people might have that question. The simple reason is that if you have direct function calls in a microcontroller sort of environment, you might end up on a path, on a chain of calls that do not terminate at a particular point in time. What this does is that it keeps your execution context time constrained. And there are a few other, for example, we have guidelines that you cannot do waits or unlimited waits on a module, on an event, sorry. And in an event, you cannot do an unlimited chain of calls of functions. You have, once you move from one module to another, you've got to generate an event targeting another module. So it keeps the code very simplistic. It keeps the execution flow broken up into small chunks What that does is that it reduces the load on the application, on the processor. So even on a small Cortex M3 class of device, this thing runs pretty smoothly. And we have moved the entire Juno code from a standard function pointer based interface to this, and it runs pretty nice. And the upside is you don't need locks, simply because you are not sharing any data between different modules. Everything has been passed as an event, so there are no locks at all. We don't use any mutexes, we don't use any other locking mechanisms at all. I think you have a question there.
Yeah, you just say that you move the Juno Porker processor to that, compared to function call to this. Have you done some performance comparison or memory, or I mean, have you compared the result?
So we initially thought that we'd run out of memory, but the answer is no, we haven't run out of memory. It's still very constrained. It's still within that 70-80 KB limit. Yes, we have a certain larger memory footprint, but that's because of the way the module-specific data or the configuration of the modules are generated and not by the code in itself. As far as performance is concerned, I'm not very sure as to what the exact overheads are. There is a certain small amount of overhead, but it's not very large considering the entire scheme of things. Because if you're talking of something like, let's say, having a spin lock or a mutex all across the code, the performance penalty of just you doing that as compared to the overhead of sending an event is like, it's a very close call. At least we have not noticed any significant degradation of platform performance even now. It boots fine. It boots at the same rate. So when you boot up the system, that's the major part, right? Because a lot of events get sent and a lot of bind functions happen. But an old code as to the new code, the boot up time is still the same. So that's what events do. Notifications are something of the other kind. So notifications are something that are sent between modules. So as a module, you can register to a notification from another module. Let's say you want to know when a system goes down. Let's say you have a dependency on a power domain and you are a clock module and you are interested in being notified when the power domain goes down. So when the power domain goes down, it just sends a blind notification. So the good thing about this is power domain doesn't need to know who are interested in it. That means your dependency chain generation happens implicitly. So every module who is interested in some other modules just registers for a notification, and that's it. And the power domain which goes down will just ask the framework, hey, send my notifications through, and the framework will send notifications to all interested parties. So what happens then is that your code is very nicely bifurcated, and it's split into nice logical pieces. So then if you remove this power domain, this power module from your module and insert a third-party module now there, it still works. Because it will still send out the notifications and the framework will do the due diligence and it just works. There was one part I missed out on the event response. So whenever an event gets processed by somebody, it sends a response. It sends a response back to the person who had generated the event in the first place, or the entity who had generated the event in the first place. The response can be a delayed response, a standard response. Standard response means the moment the event is done, the framework gives an automatic response to the entity that generated the event. A delayed response is generated when you don't want to respond immediately, but maybe at a certain point in time in the future. So that's the function, that's the capability that the framework provides. It's implemented a little bit differently. I won't go into the details, but that's what it is. Essentially, it's both the same things. One is delayed, one is not. I've got flowcharts over here, but unfortunately, I will not have time to go through it. I've kept them in the slides so that if you want to pull up the slides and then you want to reference them at a later point in time, you are free to do so, and then you can compare that with the code and figure out how it works. Be cognizant of one fact, though, that a lot of steps in these flowcharts are abstracted states. So all of them are not like single function calls. There might be multi-function calls involved in one of those boxes. So just be cognizant of the fact when you go through the code. So typically, for creating an event, if you want to create an event, you use a put event API, and that creates an event for yourself. You don't have to do a lot of things over there. And so that's what it does. And then if you want to process an event, this is what the framework does to process an event for you. So the good thing about passing events is that the generating module does not need to target the module to which an event is generated for. The framework takes care of it for you. So you just need to do a put event, and that's it, you're done. The framework will do the required steps automatically. We'll come to threading. Now, this is an interesting feature because in our previous code, we had a multi-threaded option. So we had lots of threads running, and then there were issues of deadlock, and there were a whole host of other issues that caused a lot of complications in code. And then we figured out that there was a very simple mechanism. We could just have a single-threaded model, and it worked fine. I mean, the single-threaded model works fine even with DVFS with the full system on. So that proves it. And you could have a multi-threaded model, but that's sort of an overkill, but you still have the option to do it. We have a build flag to which you can do it. So our features is that we support soft real-time scheduling on SCP. There's no hard real-time scheduling requirements. We don't have them from any of our partners, so we don't implement it. And we support cooperative scheduling for CMCs, for like in CMCs compliance, RTX, RTOS. So we don't have preemptive scheduling at all. It's all cooperative. What means is that each module, after doing its task, because it's all in events, so moment an event processing is complete, automatically the task moves on to the next thread. So the framework does it for you. So there's no need of preemptive scheduling at all. So since it's broken down into events, and an event gets tagged to a particular thread, which gets targeted to a specific module, it all works very nicely, and you don't have to do any preemptive scheduling at all. So if you look at a single threaded model, you'll notice, and if you go through the code, you'll notice that there are no threads at all. It's just the main function in a for loop, and that's it. It's as simple as that. There are no threads, and all the overheads due to threading are removed, because simply we have moved to an event-based model. There's no multiprocessor support now. We might put it at a later point in time if people ask, but today we don't have a requirement. It runs on a Cortex M3, and there's simply no need of an MP support. And the fourth thing is that there's an independence from direct RTOS calls. We have threading APIs that are mapped to CMSIS for now, but if you want to implement multi-threading, and if you are insistent on implementing multi-threading and you have your own RTOS, you can just map those APIs to your own RTOS specific APIs, and you're good for the day. The other thing is that if you use a single threaded model, you implicitly don't need any locks. And because you are event-based, you implicitly don't need preemptive scheduling. And the code becomes really simple. If you look at the single-threaded code in the code base, you'll notice that there's nothing in the code at all. It's just a 200-line file, and that's it. So you have to put the build has no multi-threading. That shouldn't be defined, and that's your single-threaded mode. And the framework thread is the only thread that runs. When we say it's framework thread, it's just a for loop. It's nothing more than that. And modules don't have their own thread. We have an event queue. So the event queue is when an event gets generated, pushed onto the queue, and it gets processed in order. And when an interrupt occurs, that's the nice part of it. When an interrupt occurs, your ISR handler gets hit, and then you can generate an event for your bottom half processing and push that into an interrupt event queue, which gets emptied out as and when your main queue gets emptied out. So that's the small flowchart that we have. And this is the simplistic scheduling model that we have for single-threaded mode. It works nice, at least on a mobile phone type environment. This thing works. There are no issues. Okay, so this is how it works. If you see that you have a queue of interrupt events, let's say M12 and M7 are the modules, and I2 and I1 are your interrupt events. So you see, and your queue of framework events are empty. So that means your interrupt has generated 2 events onto your interrupt event queue. So it goes in order. So you push your I1 into your framework event, and then you process that. And let's say, so this I1 further generates 2 events, and you continue processing them. So that means you keep processing the framework events till they are empty. So you go in a loop, and your framework queue event gets empty, and then you take your interrupt queue event again, put it there, and that's it. So it's a very simplistic model. And then we have this multi-threading mode. It's a bit of a misnomer because it's.
Can you come back on the previous? So why have you decided to treat the normal event generated by the first interrupt before processing this second interrupt event?
Yeah, okay.
Why this order?
Okay. So, okay, let's go back. Let's say initially we have something like this. Don't know which direction I'm going. Let's say this, right? So over here, I1 and I2 are 2 interrupts that occurred in order. I1 occurred first, I2 occurred next, right? So I1 is the bottom half of the first interrupt. So that gets into your framework event, and that needs to be completed first before you move on to the next interrupt processing. Because over here, we are making no implicit assumption as to what needs to be done over here. Because from an SCP perspective, it might be a DVFS interrupt, it might be a thermal interrupt, you don't know what it is. So that's the reason why we are completing the framework events first and then moving to the next interrupt event generated by the bottom half, because there is no implicit ordering involved over here. So your power request and your clock request both have a same priority order. We are not going to move around that order at all. So this. Multi-threaded mode is a little bit of a misnomer because there are no threads over here, frankly. There are threads, but the thread function pointer over here is a standard function pointer that the framework provides. You cannot provide your thread body. The framework provides the thread body. Then what's the use of multi-threading? The only difference between single-threaded and multi-threaded mode is that single-thread, everything is in a for loop. In a multi-thread, your module can specify its own thread. So you might say that let my UART have a thread of its own, and that's all you can tell the framework. And the framework will generate a thread for your UART. It will generate one for you, and then every event will be processed in your own thread context. And it provides a few benefits, like you could make blocking calls from your own thread so that if your thread gets blocked, big deal, the framework moves on to other threads, but that's about it. That's the only functionality it provides. There are no significant advantages over it. Your code might look a little bit prettier, but otherwise it's better than a single-threaded mode because all the threading, the complete threading architecture gets removed. So if you are working on a single-threaded mode, if I go back to the first slide, this particular box at the bottom, where it says architect-specific implementation and it says threading, the entire box gets removed if you're on single-threaded mode. You don't have to implement that at all. So it's a lot of advantages moving to a single-threaded mode than a multi-threaded mode. So how does it work? So let's say initially your queue is empty, let's say. Okay. This is your queue. So you have 3 interrupt events, and the common thread is the thread that runs always in the system. If your module does not have its own thread, then everything gets executed in the common thread context. So you take the first event, and let's say that gets done. You take the second event, and let's say the second event generates an event targeted to another module that runs in the context of another thread. So you then invoke that particular thread, and once that gets done, you probably get another interrupt event that comes to the back of your queue. You continue the process till the entire thing is done. So it's pretty simplistic. It gets your work done in a way that if you want a thread for your module, you can have it, but there's no hard and fast requirement. So cool. I think I'm running ahead of time. Guidelines for module design. So this part is important because if you're working on a new SCP framework and you want that to be on your microcontroller or let's say in any other environment, you just need to take care of a few design guidelines and you're good for it. So is that if you're providing generic modules, it must support both single-threaded and multi-threaded mode, which means if you're supplying a module that everybody is supposed to use. If it's just for your product, do whatever you want. Module should not block in single-threaded mode without a timeout. That's the first thing we insist, because if you block in a single-threaded mode, you block the entire system. So if you need to poll on an I2C, poll, but have a timeout of whatever you require. Do not provide long-running tasks in caller context. What that means is if you want to have, let's say, a sensor read, and a sensor read needs to go to a PMIC, which eventually goes to an ADC, and the ADC has a further chain that blocks and waits for a reading to complete and then convert. Don't do it as a single event. Convert that sensor read into one event for the PMIC, one event for the ADC, one event for the conversion, so that everything gets done in chunks. So that advantage is that if the other event comes late, there are other events which can be processed in its stead. So the system still keeps running. It's like a pipeline. The more you chop it, the faster it is. The more your blocks are. So you have a 3-stage pipeline and a 5-stage pipeline. Just it's something like that. Modules should not have shared context with other modules, which require locking. We do not enforce that in the framework today. So if you do share data structures between modules, you won't get an error. But we do insist that you do not do that because we don't have locks. But eventually, because modules only call each other's APIs, they do not have access to each other's data structures. You shouldn't be eventually be doing that. I mean, it'll require a lot of trickery to share context between modules. So you don't do that. And modules should not use allocate memory, which will not be freed later. So we do not have a dynamic free memory API. It's all statically handled. So those are the only steps that you have for generating modules. And once you generate your own modules, you can have your own system as you wish to. So what is the status currently? We support the new N1's reference design, the SGM775, the SGI 575. One is an infrastructure segment. The M is the mobile segment. The latest SCP release is 250. You'll find all of them supported over there. SCP idle is under design, so you potentially can turn off your power microcontroller also and turn off your entire platform if you wish to. Now this is under design. A few things to be done there, but we would be able to do that. So the SCMI protocols, there are a few issues with that today. It supports only multi-threading mode, doesn't support a single-threaded mode. So that is something that we are fixing. It'll get fixed pretty soon. And full power management support on a reference hardware. We have the Juno for that. We unfortunately do not have other platforms that actually do power management on an end board. So for that we have a target till the end of the year. So you should then be able to see a full-fledged power management system working with an SCP. So everything over there, including thermal and sensors. So we have PVT sensors, we have thermal sensors. We'll implement both of them, and DVFS power domains clock sensors are anyways to be implemented always, as always. What I didn't add over there, and I should have, is suspend, which is also supported, and shutdown, reset. And then finally, we are going to enable SCP firmware as a secure world resident firmware. So even if you don't have a microcontroller and you want to get this running on the trusted side, on the secure world, then you could do it as well as a library. And there are various modes and options of doing that, for which we have a session tomorrow. And you're welcome to attend that. And that work is ongoing, and hopefully we'll have some closure on that soon. And that's your specification, and that's where your firmware is again. And the slides are there. I didn't go through the flowcharts. Please have a look at the flowcharts yourselves, and hopefully you'll find this useful. So I don't think I have any more slides. We have a lot of time. So questions?
Okay. One question is that SCMI is just define the interface between the AP side and the MCU side. But how about the interface defined between the MCU side with the power controller side? So there have any definition, or this is very flexible or not? Because I know that if you want to apply this firmware to every different SoC vendors, they also need to hook the power controller related the interface into this firmware.
Okay, so the first question, so when you say a power controller, what do you mean by it? Because when we say the interface between the let's say the Cortex A and an MCU, we mean that MCU is a power controller. So are you talking of a third power controller as well?
Yeah, so this, I think that there have many different things. So I think that for this implementation, that MCU were to directly to control the CPU's power or the cluster power.
Yes.
And sometimes the SoC may be designed, they have some dedicated power control management the logic. So MCU also can works as the with the power controller to do some of the power management. I'm not sure what's the if it can be compatible or.
Okay.
Yeah.
So for SOCs which have a power management logic, which are like fixed functional domains, sort of. So you could still use an SCMI. So if you say you have a power controller which is a power management logic or an FFH hardware logic, right? Now that has to be mapped somewhere into the host, right? So you're either going to map it to an MCU or to the Cortex-A. Now if you map it to the secure side of the Cortex-A, then you'll be able to use it in the on the fifth bullet, which is our implementation of this on the secure side. So if you have mapped your logic on the secure side, you'll be able to use it like that. And if your hardware or your logic gets mapped to the MCU, then our standard implementation will work, because this MCU then goes to there's the PPU control logic, there's a PSU control logic. All of these are registers that are mapped onto the MCU space in our reference implementation that we have for the first. For the fourth slide you see on Juno board, everything gets mapped to the MCU. So there is a separate power controller which is mapped to the MCU. By power control, we just mean the logic, not anything else, right? There's no microcontroller down there. And if it gets mapped to Cortex-A, that's your bullet 5. So either way, it'll work. And if you want to daisy chain this, right? If you have, let's say, one MCU and then say another MCU, you could even do an intra-MCU communication within using SCMI. That's also possible.
So, okay, I almost understand what you mean. So here I have one thing that for this case that still that from the AP side, the normal non-secured still need to call SCMI interface to the secure world.
Yes.
Then secure world will to use what the interface to interact with the MCU firmware. Also use, I mean that here I'm not clear. What's the SCMI, this protocol will be used in the normal world, the Linux kernel side, or it will be used in the Arm trust firmware this side?
Okay, so for that it's tomorrow's session. Tomorrow we have 2 sessions back to back, one which explains you the different SCMI deployment configurations, and the next session which talks about the ongoing project that we have with STLinaro and ARM for the secure side implementation of the SCMI server. So all those configurations we'll talk about on tomorrow's session in complete detail. I think that's a question there.
So in the boot flow, who loads the SCP firmware?
It's when you load the firmware is loaded initially by I think BL1, and BL1 is I think TFA.
It depends on the segment actually. So on the mobile, the SCP ROM boots first, and then it releases the application core, which then loads the runtime SCP.
Yeah.
Okay.
For the enterprise, SCP loads directly and loads its own runtime firmware. So it depends on the segment.
Okay.
Yeah. You can build the way you want actually. Yeah.
Okay.
Yeah.
If I capture it correctly, previously you also mentioned about the SMP, if I capture it correctly. So how does that work together at system level, like the whole SOC level? Is it a management processor? System management processor?
This is okay. You're talking of SMP or you're talking of
SMP.
MCP?
SMP.
So this is not SMP capable.
Right, right. So I misunderstood. I may misunderstood what that means. Like, is there a SCP plus SMP or not?
No, there's no
Okay.
SMP SCP support today at all. It's a uniprocessor support on the SCP firmware that we have today. We do not support multiple cores inside the SCP.
So within SOC, there's a AP and there's this SCP.
Yes.
From a SOC's point of view, would this SCP consider as secure, non-secure, or how does it work with AP?
It's a power controlling. It's a power controller, but whether it's secure or non-secure, it is not the root of trust. SCP is not a root of trust. It's secure in as much as you can make it secure because you are giving it control of your system power resources. So if you, let's say, put a device voltage into a unsteady state where the device goes for a toss, so in that sense it's secure, but SCP is not the root of trust of the system.
Mm-hmm. Okay, thanks. I guess it's also related to the previous question about the boot flow.
Yes.
How it being partitioned in enterprise versus mobile. How
Yes.
about
so in enterprise we have an MCP, the concept of an MCP. That's related to the boot flow as well. So the enterprise works a little bit different from the mobile. What I explained over here very nicely is what it works on a standardized system, and all of these examples are of a single SCP. The newer version might have an MCP that you can build as well, but currently we don't have a lot of other examples. Frankly, most of these are single SCP configurations.
Thank you.
Yeah.
So when we promoted the SCP to China partners, one question was also asked to me. So in Juno, we upgraded the M4, Cortex M3, M4 to the Cortex M7.
Yes.
So how do we measure the computing power, and what's the justification to upgrade to M7?
On Neoverse. You're talking of Neoverse for M7?
No, just for SCP. Or for SCP or MCP is upgraded from Cortex M3 or 4 to M7.
If you were to do that. Sorry, I didn't understand. You're talking of a theoretical upgrade or an actual upgrade on a platform?
So actually in Neoverse now
It's
it is
M7,
Cortex
yes.
M7. So
Yes.
yeah, why we have to use the
Okay,
M7?
because that's an infrastructure device. You could have more than 100 cores because it's a reference device, so it just has 8, but you could as well as have 100
Yeah,
cores.
so the question is, how do we benchmark the computing power? So do we have any benchmark or any methodology to?
Yes, okay, I get you. I get your question. So we have internal benchmark when we moved from M3 to M7. We did internal benchmark before we arrived at the core, but that has not been open sourced. We have a lot of plans to now get this optimized for power and performance, and then get, let's say, power rest to performance ratio calculator or something that tells you that for your particular platform, this should be a reference speed or the reference IP that you should use. But that, we are not at that stage yet.
Okay, so because M7 is a bit expensive than M3, so do we have any test result or data about the M3 or M4 can support how many AP cores? For example, 16 or 24?
Okay, so I
Yeah.
think that
just a reference,
Yeah,
maybe.
yeah.
Yeah.
I'll tell you. So it easily supports 8 cores. There's not a problem there. The bottleneck comes with DVFS. So if you do DVFS in a bursty application, which generates, let's say, a DVFS request every one millisecond, or within the fraction of a 1 millisecond window, it generates a lot of them, then that's the point where you have an overflow, because the DVFS loop is really long, and you've got to do a lot of calculations before you can even set a PLL or a clock, right? So that 6 to 8 cores is what it manages till now. And we haven't been able to move further than that because we haven't emulated any more cores. But an M3 running at 50 megahertz is sort of a sweet spot for 6 to 8 cores for Android, where it does a lot of DVFS transfers. For infrastructure, you don't have a lot of DVFS transfers, but you might require the bandwidth for something else. So there are a lot of C6 configurations that go on in the SCP. There are CMN600 specific cases as well. So for infrastructure, the requirements are different. For mobile, the requirements are different. I think you want to add something.
I want to just complement that. Yeah, so because I was working on that project at that time, there was also things like the MPU for the Cortex M7 was better. It had more regions you could define. I believe the number of interrupts is also bigger.
Higher,
which,
yes.
yeah, which for the enterprise or for the infrastructure,
Yes.
it was a requirement actually at that point because you had more clusters, more CPUs.
Yes.
And the throughput was also bigger. the clock could be higher, and you could afford because it's an enterprise
Yes.
chip.
It was
That
purely
was
an enterprise play. It was never a mobile play. So on mobile phones, you don't need an M7 class. It's an overkill.
Okay, so the second question is, just now you mentioned that the SCP design should be agnostic. So if the customer want to replace the Cortex-M or M3 or M4 or even M7 to another customer-specific SoC, so
Yes.
do you know, what's your comments about the porting efforts? So is it difficult or is it likely or not likely?
Okay, so all you need to do is replace the slower box in red. So if you're using a single-threaded mode, you just have to enable your interrupt redirection. That's enabling and disabling your interrupts. And memory management it's pretty simple. So if you're looking at have your own course, right? All you'll probably have some medium-ish sort of effort. It's not trivial, but it's not large either. You can support a completely different. So if you want if you want to deploy it on a Spark core, then whatever you need for implementing those two specific modules, you know the requirements and.
Okay, that's great. Yeah, thanks.
Just a curiosity. So when we started, the architecture, it was actually running on a normal desktop. So threading was simply the normal thread you would have on a desktop. It didn't have an interrupt, and memory management was just a malloc. Because the framework is pure C, so you can just rebuild it on your desktop, which was.
Yeah. You can even run it on a host. I think we are out of time. The screen's blinking at me. Thanks for coming. And if you have any questions, do get in contact with us, or you will find the maintainers page in the SCP. Get in contact with those guys, and we'll be happy to answer any questions that you might have. Thanks, everybody.